Hello students, today I am going to discuss with you the concept of branch and branch points of multiple valued functions. So what are multiple valued functions? So a function of a complex variable w is equal to fz is called single valued if for every value of z there is one and only one value of w. For example, w is equal to z. When you put one value of z in this function, you will get one and only one value of w. Similarly, the functions fz is equal to z square or fz is equal to z raised to power n, where n belongs to natural numbers, and the functions sin z, cos z, ez, these all are example of single valued function. So on the other hand, if more than one value of w corresponds to each value of z, that is, when you put one value of z, you get more than one value of w corresponding to that value of z, then the function is called multiple valued. For example, w is equal to z raised to power half. If you put any value of z, say z is equal to 2, then you get two values of w that are plus minus under root 2. So this is a multiple valued function. Similarly, w is equal to z raised to power 5 is a multiple valued function, and z raised to power 1 by n is also a multiple valued function, and corresponding to each value of z you will get n values of w. So now what is branch of a function? A multiple valued function can be considered as a collection of single valued function, and each member of which is called branch of the function. For example, w is equal to z raised to power half is a multiple valued function with two branches. W is equal to z raised to power 1 by 5 is a multiple valued function with 5 branches, and each branch is a single valued function. Now I want to discuss in detail some example of multiple valued function with its branches. In my first example, I have taken the function w is equal to z raised to power 1 by 5. For the representation of this function, we use polar representation of the points. Now take z is equal to re iota theta. Take a point z1 in z plane by taking z1 is equal to r1 e iota theta 1c. Then we make a complete circuit counterclockwise around the origin. First we put this z1 in the function w. So w will have the value r1 raised to power 1 by 5 into e iota theta 1 by 5. After we make one complete circuit about origin, theta 1 changes to theta 1 plus 2 pi. So w will change to r1 raised to power 1 by 5 e iota theta 1 by 5 into e iota 2 pi by 5. That is, argument of w changed by 2 pi by 5. So w will take the new value, say w2, and this new value w2 is different from w1. That is, we are not reaching at the same point after making a complete circuit around the origin. So when we again make a second circuit about the origin, that is, theta 1 changes to theta 1 plus 4 pi, then w will take the value r1 raised to power 1 by 5 into e iota theta 1 by 5 into e 4 pi I by 5, and which is again different from the previous point w2. So let the value of this w is w3. Now if we make third and fourth complete circuit around origin, we get the value W is equal to W4 and W is equal to W5, which is equal to W1E 8 pi I by 5. But when we complete the fifth circuit about the origin, then we get that the value of the W will again becomes W1. That is, now we are reaching at the same point from where we have started, but after making 5 complete circuits around the origin. So it means that now we are on the first branch of the function again. So the 5 different values represents the values on different branches of the function. So it means that our W is a 5 valued function, 5 valued multiple valued function. And to remain on the same branch of the function, we have to restrict our theta. Suppose we are restricting the theta, that is, theta is greater than or equal to 0 but is strictly less than 2 pi. It means that the line theta is equal to 2 pi acts as a barrier, and if we cross this once, then we are on the second branch. If we cross this line theta is equal to 2 pi by making another circuit, then we are on the third branch, and after repeating it 5 times, we are on the same branch of the function. So for different branches, we have to restrict our theta line. That is, we can consider W as a collection of 5 single valued functions, and those 5 single valued functions are called branches of the multiple valued function. And thus we can write W as R1 raised to power 1 by 5 into cos theta by 5 plus iota sine theta by 5 by taking 5 possible intervals for theta. First possible interval is given by theta greater than or equal to 0 and less than 2 pi. Second branch can be obtained if we restrict theta greater than or equal to 2 pi and less than 4 pi. For the third branch, we have to restrict our theta must be greater than or equal to 4 pi, less than 6 pi. For the fourth branch, theta lies in the interval 6 pi but strictly less than 8 pi. And for the fifth branch, theta must be greater than or equal to 8 pi and strictly less than 10 pi. So in this way, we can find 5 branches of this multiple valued function by restricting our theta properly. And this theta is equal to 2 pi line acts as a barrier for the multiple valued function to get different branches of the function. But this barrier theta is equal to 2 pi line is not a unique barrier. We can also consider some other restriction on the theta. For example, if we take that theta is greater than or equal to minus pi and strictly less than pi, theta greater than or equal to pi strictly less than 3 pi, theta greater than or equal to 3 pi and strictly less than 5 pi, and theta greater than or equal to 5 pi strictly less than 7 pi, theta greater than or equal to 7 pi strictly less than 9 pi. So for these 5 intervals also, the line theta is equal to pi acts as a natural barrier for defining different branches of the function. Now I would like to define the concept of branch point. So what is a branch point? A point around which we make complete circuits to find different branches of the multi-valued functions is called a branch point. We can also define branch point using the analyticity. So, the point where the multi-valued function w is equal to fz is not analytic is called a branch point. So, we have two concepts to find the branch points. First is that if we make a complete circuit around the point and completes after making complete circuit we are on different branch of the multi-valued function, then the point will become the branch point around which we are taking the circuits. And another way to find branch point is that if we know that a function is multi-valued, then you just simply differentiate the function and find out the points where the function is not analytic. Then those points are called branch points. For example, w is equal to z raised to power half. You know that its derivative is 1 by 2 root z. Then you know that this function is not analytic at z is equal to 0. That is, this function is analytic everywhere except z is equal to 0. And you also know that this function w is equal to z raised to power half is a multi-valued function. So z is equal to 0 will act as a branch point of this function. In a similar way, we can prove that the function w is equal to z raised to power 1 by n, where n belongs to natural minus 1, that is n can take the value 2, 3, 4, 5 and so on, is an n-valued function with n branches, and here also 0 will act as its branch point. After that, there is another concept of branch line. So what is a branch line? A branch line or a branch cut is a line on the z-plane originating from the branch point, and the line acts as a barrier which we do not cross in order to remain on the same branch of the function. That is, the line which is originated from the branch point and can have any length is called a branch line or branch cut if we cross this line and then we are on, if whenever we cross this line we are on another branch of the function. For example, in case of w is equal to z raised to power 1 by 5, the line theta is equal to 2 pi act as the natural barrier, and hence it is a branch line or branch. Theta is equal to 2 pi. The line theta is equal to 2 pi is the branch cut of the function z is equal to w is equal to z raised to power 1 by 5. Now as we know that the branch points are the points where the function's derivative does not exist. That is where the function is not analytic. So these points are also called the singularities of the multi-valued function. One thing you will notice here that no point other than 0 is a branch point of the function w is equal to z raised to power 1 by n, because you can see here that if you take any point different from 0 on the z plane, say z0, and you make a complete circuit about z0, and let us take points f a b c d e on the circle, and when we move to the point from F to A to complete the circuit about Z0, you can see that the angle theta changes to theta 1. After that, when you move to point B, the angle changes to theta 2. And similarly, when you move through the points C, D and E, the angle changes to theta 3, theta 4 and theta 5 respectively. But when you completed the one circuit and again reached at the point F, then theta takes the same value. That is, theta 5 becomes theta only. So it means that there is no change in the argument of theta when you start from the point F to make a complete circuit about Z0. After completing the circuit, you remain with the same value of theta. So you are on the same point and on the same branch because there is no change in the argument of the point F. So it means for the function w is equal to z raised to power 1 by n, 0 is the only branch point. In a similar way, we can find the branches of the function w is equal to z raised to power p by q, where GCD of p and q is 1. I have explained in the example the different branches of the multi-valued function, and I have done one more exercise for you, taking the function w is equal to z square plus 1 raised to power 1 by 2. And in this exercise, I have solved two problems. The first problem is that find the branch points or show that z is equal to plus minus eta are the branch point of the function. And the second problem is show that a complete circuit around both branch points produces no change in the branches of fz. So, first, to solve my first problem, I have to prove that z is equal to plus minus eta are branch points of the function fz. So there are two approaches. One approach is that first you show that the function z square plus 1 raised to power half is a multi-valued function. And then you show that the function w is equal to fz is not analytic at the point z is equal to eta and z is equal to minus eta. So these points will become the branch point of the multi-valued function fz. Another approach is that you show that when you make one complete circuit around the point z is equal to eta, you are on a different branch of the function w is equal to fz. That is, you are not getting the same value from where you have started. The argument changes. So we have two candidates, namely z is equal to eta and z is equal to minus eta for the branch points. Now let the polar representation of the points z minus eta is r1 e eta theta 1 and the polar representation of the points z plus eta is r2 e eta theta 2. Then substituting in the function w is equal to z square plus 1 raised to power half, we get w is equal to r1 raised to power half into r2 raised to power half e eta theta 1 plus theta 2 by 2, and say this value is w1. Now make a complete circuit about z is equal to eta, because we want to show that z is equal to eta is a branch point. So when we complete one circuit about z is equal to eta, we get that theta 1 changes to theta 1 plus 2 pi. So we get W is equal to R1 raised to power half R2 raised to power half E iota theta 1 plus 2 pi plus theta 2 by 2. And when we evaluate using the fact that E iota pi is minus 1, we get W is equal to minus W1. So this is not equal to W1. So this implies that after making one complete circuit about Z is equal to iota, we get a different value of W. That means we are on a different branch of the multi-valued function. This implies that this point Z is equal to iota is a branch point. And in a similar manner, we can prove that Z is equal to minus iota is also a branch point. And now for the part 2 of the problem, we have to make one complete circle enclosing both the branch points, and we want to prove that there will be no change in the value of W in this case. So why? Because when we enclose these 2 points Z is equal to iota and Z is equal to minus iota in one circuit only, then theta will change to theta 1 plus 2 pi, theta 2 will change to theta 2 plus 2 pi. So argument of W will change by 2 pi. That means change in argument is 2 pi, and we know that the value of E iota 2 pi is 1, so there will be no change in the value of W when we make a complete circuit when we make only one complete circuit enclosing these 2 points. So we are done with the second part also, and now there are two problems which you have to solve. In the first problem, you have to prove that Z is equal to plus minus iota are the branch points of the function Z square plus 1 raised to power 1 by 3. And in the second problem, you have to find the branch points and construct branch lines for the two functions. So I hope you will easily do these two exercises. It is enough for today's lecture, and tomorrow we will discuss the branches of the multi-valued function log z. So thank you.